Okay. Uh, Hello, everyone. So I think with 3, 4 participants, let me wait for another. Okay. Hmm. Anyway, hopefully others will join. So yes, now we are in Fourier analysis. Okay. So so can you listen to me? Somebody reply. Can you? Others? Is the audio clear? Somebody reply in chat or verbally. Hmm? Okay. Okay, Rajesh. Thank you. Okay. So yes. Okay. So I think enough participants are here. Hmm. Yes. So now we are into Fourier analysis. So the topic that we finished was time domain analysis of LTI systems. Okay. So what I would suggest is it is partial module 2. Now this Fourier analysis is a part of module 2 only, I guess. Okay. Hmm? So module 3, sorry. Okay. So what you can do is for module to the the LTI systems and all, you can go through hiking the textbooks or Uday Kumar or all those textbooks and solve some problems and be comfortable because of the lack of the board and lack of the interactivity. I'm limiting the number of problems that I can solve. Okay. Anyway, what we'll do today is we'll get started with this Fourier analysis. So the topic is going to be uh, interesting. Okay. So let us see how does it go. Yes. So yesterday we had started this thing, right? What is the use of a Fourier analysis? And we had something. So what was it, by the way? Yesterday we discussed this thing, right? If at all you happen to have a system with the different frequencies and you don't know which all are those frequencies present in that particular system and what is the contribution amount of power in that, what you can do, you simply take the Fourier transform and you will automatically come to know. Whenever I take a Fourier transform, you will see a signal and its replica on the second half also. Okay, neglect it. We will consider it as and when the time comes. Okay, we will address that issue later. Okay, so one of the application was predicting the different frequency components and their contribution. Second thing which we did yesterday was to learn the role of this equalizer in any audio player. Okay, so this thing is also a sort of frequency domain manipulation only. You observe this non-linear scale. That is what even our behavior is, right? We are accustomed to this non-linear behavior of audio. We have been drawing all semilog graphs and all, right? Yeah, that's one of the reasons. Okay, audio synthesis, what only. And the third one I was telling is the ease of performing a convolution, right? Having Fourier simplifies the whole purpose of a convolution. It converts convolution into multiplication. Now you might wonder, what's the big deal with convolution? Now see here, here is an expression for convolution. What does a convolution actually contain? It contains multiplication, it contains lots of shifting. You have to shift, you have to multiply, then you have to integrate. Here also shift, multiply, summation, shift, multiply, summation, right? So instead of shift, multiply, summation, if at all you take the Fourier transform of x of t, say x of omega, Fourier transform HCC x of t, if you take the Fourier transform z of t, you take the Fourier transform, then convolution becomes just a multiplication. Convolution just becomes multiplication. So instead of just multiplication, then the shift and then the integration, or multiplication, shift and summation, you can manage with only multiplication, right? So that would be a very, very big advantage. That would be a very, very big advantage, and makes the data independent of the length of the data, makes the operation independent of the length of the data. Of course, there is an overhead of taking the Fourier and taking the inverse, but compared to the kind of complexity in simplicity it provides, it is a negligible thing. So that was that. And then the last advantage that you spoke about was the frequency response. You can always predict the a frequency response. Okay. So frequency response means for what frequency, how the signal is going to behave, right? Yesterday we discussed this. What is meant by frequency response? Frequency response means probably you want to know at which frequencies, right? Now suppose you happen to have an LCR circuit which is going to give a very good gain at a particular frequency and a very high attenuation at a particular frequency. You want to know this, right? You have the LCR circuit, right? You have the LCR circuit. You want to know the resonant frequency and the anti-resonance frequency. What you have to do is simply take the Fourier transform of that LCR circuit equation, right? LCR circuit equation means what? Take the LCR circuit, represent the circuit in terms of a differential equation, take the Fourier transform, and from the Fourier transform you find out the impulse response, take the Fourier transform, you get the frequency response, then you simply plot it. You will come to know at what frequency how much gain it is going to give. Okay, so I think all these reasons are sufficient for us to be curious in Fourier analysis. Okay. So now the Fourier analysis. So there are actually 4 types. Okay. So everybody, now we have started, right? Okay. So please listen in carefully. Okay. So the thing with Fourier is all about not getting confused. Okay. Let me tell you once again. The thing with Fourier analysis is not to get confused. It's all about having things as much clear as possible. Okay, let me tell it to you now itself. Okay, so listen in carefully. Okay, so what is there in Fourier, by the way? So Fourier is all about converting data from time domain to frequency domain. You have had this Laplace transform which will convert from time domain to S domain, and you might have studied this Z transform also, which will convert from time domain to frequency domain, right? Sorry, the Z domain. This is a specific extension of your Laplace. You replace your S by e to the power j omega, S by j omega, your Laplace transform. Okay, so if I saw just now in your control systems where I shared a notes, if at all you simply replace S by j omega, if you replace S by j omega, your Laplace transforms becomes a Fourier transform. And if at all you simply replace Z by e to the power j omega, if at all you simply replace Z by e to the power j omega, then your Z transforms into Fourier transform. Okay, that is the relation. Now this one is a very specific transformation. Okay, which translates from time to frequency. Okay, that is why we communication engineers are much more interested in this transformation. Okay. So now what sort of signals can be there, by the way? So there are 4 types of categories. There is Fourier series and there is Fourier transform. Okay, periodic signals will have series. Periodic signals will have Fourier series. Non-periodic, aperiodic signals will have Fourier transforms. Okay. Periodic signals will have Fourier series. Aperiodic signals will have Fourier transform. Continuous signals will have continuous time Fourier series. Discrete time signals will have discrete time Fourier. Okay. If it is discrete time periodic signal, it will have discrete time Fourier series. Discrete time aperiodic, then it will have discrete time Fourier transform. Okay. So there are 4 types of things. There are Fourier series for periodic signals, Fourier transforms for aperiodic signals. So now here in this particular module, what we'll do, we'll start with Fourier series. Okay, so we'll talk about what sort of signals: continuous time periodic signals and discrete time periodic signals. For continuous time periodic signals, we'll have Fourier series, or what they call continuous time Fourier series. For discrete time periodic signals, we'll have discrete time Fourier series. Okay. Afterwards, you'll go to the next module where we will discuss for non-periodic signals. They will have Fourier transform continuous and discrete time Fourier transform. Okay. So usually whenever there is a communication taking place, if at all signals are periodic, they are usually, you might have studied this amplitude modulation or frequency modulation, right, where the data is modulated using a carrier. Now this carrier doesn't change, right, and carrier is periodic, it's a cos wave or a sine wave, right. So they are better analyzed by the Fourier series, whereas the data which is there on the carriers, right, like the news, right, news is not periodic, right, it keeps changing all the time. Now this data which rides over that carrier, the which modulates the carrier, that is aperiodic in nature, and they will be analyzed with the Fourier transform. So for this thing, so periodic signals will have Fourier series, aperiodic signals will have Fourier transform. So what we'll do for the time, we will study the Fourier series. Okay, now we'll study the Fourier series. We'll start with the continuous time Fourier series, and then we will go to discrete time once you are done with the continuous time. I will not be going into much elaborated version of the Fourier series. Even your syllabus mentions that the derivations or the properties need not be done. We'll see all those applications in Fourier transform. So I'll be doing a very little number of problems in continuous time and discrete time Fourier series, but we will use it as a bridge to go to Fourier transform. Okay, so let us get started with the first thing, the Fourier series. Okay, let's get started with the Fourier series. Okay, so yes. So for continuous time periodic signals, we have this series. Okay, for continuous time signals, periodic signals, we have this thing called as continuous time Fourier series. Okay, what is the formula, by the way? You can see here x of t equal to x of k e to the power j k omega naught t. Okay, x of t equal to, where x of k is x of t e to the power minus j k omega naught t. Okay, so okay, that is the formula. Okay, that's the formula. What does the formula do, by the way? So when you do it, by the way, now you can see here, here we will see a notation, right? This you can see is x of t only. This here we have, this is the formula. Okay, this is the formula for Fourier series. What you have to do, you will be given an x of t, you have to multiply it with e to the power minus j omega naught t. Omega naught is the fundamental frequency, t is the period of the periodic signals, and what you get is this kind of representation. Okay, this is the general representation. If at all there is an x of k coming, you come across x of k this semester, what this means is actually it is the Fourier series. Okay, so what sort of representations are we talking about here, by the way? This is usual, right? I think you are let us see a numerical. Okay, now you can see this x of t here, this x of t here has been represented in terms of time domain, right? This has been represented in terms of time domain. A nice graph is drawn. It is telling you at what time instant, what is the amplitude, right? Or maybe this particular thing here. You can see this particular thing here. So here you have been given an x of t, and you substitute t, you get to know the value at each and every instant. You can predict the behavior of this particular wave in time domain. So what we are trying to do, in Fourier is, we will try to represent this in terms of, okay, something like this here. Okay, we will represent it in terms of okay. This one would be better. See here, you can see this is one representation, right? Let me take this. Okay, this is one type of representation, right? Where you'll represent this x of t in terms of varying amplitudes with the time. This you can see is a second type of representation for the same. It's the second representation for x of t, where what you have, by the way, okay, so what is it, by the way? It is represented in terms of some e to the power jk. This is omega naught. Okay, this is omega naught, e to the power j and its multiples. You can see here, this is that e to the power j terms, and this is getting multiplied by some x of k. Okay, these are those values. So what you are trying to do here is, you are trying to represent a time domain signal in terms of the fundamental frequency and its multiples. So what are these, by the way? E to the power j theta. These are all complex exponentials. So you are trying to represent an signal x of t in terms of complex exponentials and its harmonics, right? Omega naught. So what is the contribution of omega naught, 2 omega naught, 3 omega naught, 4 omega naught, and so on? Okay, so you are trying to represent that. That's what was here, right? You saw this particular thing even in this beginning when we took Fourier transform example, right? Here you can see this is one type of representation. This is one type of representation where you tell the variation with respect to time, right? How does it vary with respect? This is one more type of representation where you are not interested in the behavior with respect to time, but you want to know what are the individual frequencies, what are the individual frequencies, and what are their contributions in terms of power or strength, I would call it. Okay. What the thing? What the thing? So this is representing a given signal in terms of fundamental frequencies and its harmonics. Okay, fundamental frequency and its harmonics. So basically, so how do we do it, by the way? So you just don't have to do much. What you do is simply apply the formula. Apply the formula and things turn out to be true. So if at all I simply use this x of k equal to 1 by t integration over a single period x of t to the power minus j k omega naught t dt, the entire signal x of t, whatever you have given or you have drawn, will be broken down into the contributions of fundamental frequencies and their harmonics. Okay, automatically. Okay. So what this particular thing? Hence the Fourier series. So for continuous time periodic signals, what we have here is Fourier series. Okay. What this thing? Now let us see a numerical setup. The moment instead of going into the theoretical thing, you see a numerical will be much more convinced. Okay. So here is a question. Determine the Fourier series of the following signal. Now this signal here is, first of all, it is continuous time. Second thing is it looks periodic. So of course it may have a Fourier series representation. What is a Fourier series representation? Author wants us to represent it in terms of this particular equation. To represent it in this particular equation, what we need to know? We need to know this particular parameter, right? Yeah, this guy here. This is what we need to know. X of k. Okay, this is what we need to know. Let us go and find that. Let us go and find that. Now I want you people to tell me. I want you people to tell me. We need to substitute this here. By the way, we need to substitute this. So please, somebody tell me. Please, somebody tell me what is the period. What is the period here? And second thing, what is the fundamental frequency? Somebody please tell me. Look at this figure here. Look at this figure here. Of course, I also know this is not so clear, but still, I think it's bearable figure. Can anybody tell me what is the period in this particular thing? Can anybody reply in chat? Or you can tell also directly on the mic. Can you tell me what is the period of this particular signal? Hmm? As I told you, be there with a scribbling pad or something like that. We want to make this as much interesting as possible. Participation is a thing that you need here. Please, somebody tell me what is the period of this signal? Anybody? What is the period of this? Looks periodic, right? What is the period of the signal? Can anybody tell me what is the period? Anybody? Hmm? Please look at the figure and tell me what is the period. Hmm? Somebody tell me the period and the frequency. Give up? Shall I continue? Shall I continue? So you give up? Hmm? Let me continue. Okay. So let me continue. Yeah. Anybody? Anyone going to tell me the period? Anybody is going to tell me the period of this particular thing? Look at the question carefully. So here he has mentioned this is t and this one is minus t. Here is a 0. This is the 0. This is minus t. This is t. Now can anybody tell me what is the period? You can see here. This is t minus ts. T plus ts. So now anybody, can anybody tell me what is the period of this particular signal? Can anybody tell me what is the period of this particular signal? Hmm? Okay, let us move then. Okay, let us just continue. Okay, 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 okay. So two things by the way. First is to determine the period of this. Okay, first is to determine the period. Now you can see this particular wave is from here to here. Now this shall be the period. What do you think is this width? Okay, now this one from here to here, t minus, okay, t minus ts to t plus ts, yeah, t minus ts to, no, this is the period is not this one. Okay, the period is from here to here. Okay, very good, nice tried. Okay, this is the period. Okay, this is the period, this is the time, this is the width of the pulse, but then after there are zeros on the right. Now you can see from 0 to t. Now this thing here, this pattern 0 to t is what that is repeating. You can see this is one pattern. From here to here you can see this is also one more pattern. Okay, so the period is t. Okay, so the period is this width. Okay, it is t. And what we will do, for simplicity, we will perform the integration from minus t by 2 to t by 2. Okay, the entire width I told is t, but then it is non-zero from minus ts to plus ts, right? So that is why this will be minus ts to plus ts. What about omega naught? If the period is say t itself, omega equal to 2 pi f or 2 pi by t. Okay, that will be the thing. So here is the solution to this. Okay, here is the solution. So period happens to be t only. Period happens to be t only. For integration, actually we should have done from minus t by 2. Okay, we should have done from minus t by 2 to minus t by 2 to t by 2. Okay, minus t by 2 to t by 2 is what we should have done. But since this is 0 here, this is 0, and this is also 0, that is why we'll stick to only this particular area, minus t by 2 to t by 2. Okay, minus t by 2 to t by minus ts to ts, sorry. Okay, omega naught, what is the value of omega naught? By the way, omega naught happens to be 2 pi by t. Okay, omega naught happens to be 2 pi by t. Anyway, let us not 2 pi by t. Okay, this is a pi. Okay, the one which I have 2 pi by t. Anyway, so simply substitute the value. Amplitude anyway is 1, so this is getting simply multiplied by 1 only. So you get a value here. So they simply substituted. We know this e to the power j theta minus e to the power minus j theta divided by 2j is a sine, right? Then you got this particular thing. Okay, this is my Fourier transform, Fourier series. There is a small problem here. That this will not give me the value at k is equal to 0, because see here, k is equal to 0. This is also 0. This is also 0. So this will be a 0 divided by 0 problem. Okay, this is a 0 divided by 0 problem. So this formula works, but not for k equal to 0. How do you find, by the way, for k equal to 0, what to do? For k equal to 0, we will substitute 0 here. Okay, at this point. Okay, at this point we will substitute 0. Then what's going to happen if this goes to 0? This entire term goes to 1. So we will have simply an integration of 1 dt. Integration of 1 dt. Okay, from minus ts to plus ts. Okay, what this is, this is very tricky question. So whenever you are given this particular graphs, so the finding the value at 0 becomes very tricky. Let us see how author has done it. Okay, how author has done it. Okay, for k equal to 0, it's simply 1 dt. Okay, minus ts to plus ts, minus ts to plus ts. So what's the answer we are getting? So it is 2 ts by t. Okay, so here is the answer. So this is x of k, this is the value. Then here still not substitute omega. Omega naught is 2 pi by t. Okay, omega naught is 2 pi by t. Okay, so this is the value for t not equal to k not equal to 0. This is the value for k is equal to 0. Okay, if time permits, what you can do is you can take your calculator and you can substitute values. But since he has not given any numbers here, if t was given as okay, hmm, if p is and ts were given as numbers, then we could have substitute. Shall we do this thing once again? Okay, so we started with this particular problem, okay, this particular numerical, and we just have to simply go on substituting this particular part. Okay, now see this particular figure here. So now this thing here, you can see this particular chunk. Okay, this particular chunk is repeating, right? This particular chunk is repeating. So what is this particular width? From 0 to this is t, this is also t, so this width will also be t. So this happens to be the period of the signal. So this t here is the period which will substitute this t. Then omega naught, again this omega naught is 2 pi by t. Okay, omega naught is 2 pi. What is value of x of t, by the way? Okay, then you integrate from all non-zero values. So when you do that, you will get, okay, so 1 by t, the period from minus ts to ts. Of course there were values here, as I said, there are this values anyway is 0, right? This is anyway 0, that is why from minus ts to plus ts, right? Or non-zero values will simply integrate. X of t is anyway, this is 1, so only this thing is what we will integrate. And once this is integrated, we will get something like this. Now here, if you had a calculator, if at all, you could have substituted, but this is a general form: e to the power j theta minus e to the power minus j theta divided by 2j. So we'll write it as a sign. Okay, so basically, whenever the given signal is a rectangular one, its Fourier transform turns out to be a sort of a signal like this. Okay, sorry, a signal like this. Okay, it's called as, okay, these kind of signals are called as sync pulses. They are called as sync pulses. Okay, they called as sync pulses. Okay, for this thing. So yeah, okay, so at 0 it is 2 ts by t, and at other values other than 0 it is 2 sine k omega naught ts divided by tk omega naught. Here what you have to do, now once you are done with this, go on substituting value of k. K is equal to 0, 1, 2, 3, 4. You will get so many values. Okay, that was about the Fourier transform. Okay, got this thing. So Hmm? So now what we'll do, we will see one more problem. Okay, so I'm sorry that I had to start with that particular tricky problem, but hmm, okay, so another 10 minutes remaining here. Okay, another 10 minutes remaining here. Now let us try and do this particular thing. Okay, now see here, there is one more question. Determine the Fourier series representation of x of t equal to 3 cos pi by 2t plus pi by 4. Okay, now here what we'll do. So in this particular question, it was a rectangular wave. Usually rectangular wave contains lots and lots of frequencies. That is why we end up getting this particular complicated thing, a sine divided by sine. Whereas this particular thing, now I think it's more of a, intuitive that this happens to contain only one frequency, right? A cos 2 pi fct plus theta, right? It contains only a single frequency. Okay, so what we will do here, instead of substituting here, what did we do? We substituted in the formula, right? We substituted in the formula. So if at all you are given any kind of a random wave which is periodic, you just have to find the period, substitute here, find the fundamental frequency, substitute here, go on doing the integration till you reach certain value where you can plot it. Okay, that's it. Okay. Now this is a typical question where you happen to know that there is only one frequency which you need to identify. So what we'll do here, for a change, we will not substitute in the expression, rather we will take this particular thing, the standard expression, and we'll try to compare. Okay. Now see here, what author has done is he compares it to this particular expression. This is x of t here, right? This is x of t. Now what author does is he compares it to this particular representation of x of t. This is the formula for inverse Fourier series. Okay, x of t in terms of x of k. So the first thing what author does, the moment you see a sine or a cos, what you do is you represent it in terms of complex exponential. Now cos theta, what is cos theta? Cos theta is e to the power j theta plus e to the power minus j theta divided by 2. Okay. So now this thing here is e to the power j theta. Theta is pi by 2t plus pi by 4 plus e to the power minus plus pi by 4 whole divided by 2. Or this is how it has been expanded. One thing you need to know is this thing here you can see in place of omega naught. Okay, first thing what you have to do is you have to find the fundamental frequency. Okay, first thing is you have to determine the fundamental frequency. Can anybody tell me how do you find the fundamental frequency? Cos 2 pi by 2, you will compare with it 2 pi fct. Okay, a cos 2 pi fct, pi by 2 into 2 is equal to 2 pi fct. So t turns out to be 4. Okay, so t turns out to be 4. So omega naught is 2 pi by t. This is pi by 2. So I substituted a pi by 2 here. Okay, substituted a pi by 2 here. And then this simple cos wave, I represent it in terms of e to the power j theta, right? The complex exponential. This is how they look like. So I have made sure that this particular thing, okay, e to the power j pi by 2t has been taken outside. See here, e to the power jk pi by 2t here, and here I have taken out e to the power j pi by 2t has been taken out. Now I will compare. So minus j is for k is equal to pi by 2 is there, pi by 2 is there, t and t are there, right? These two are there. So okay, pi by 2 and pi by 2, t is t. Then what is k? So in this particular case, k is what's the value of k? 1. Okay, so this particular term with k is equal to 1, then what is this remaining term? What is this remaining term? So this term is your x of k, x of 1. Okay, so your x at 1 is equal to 3 by 2 e to the power j pi by 4. Similarly, here in this particular case, a is equal to minus 1. Then this particular term here is your 3 by 2 e to the power j minus pi by 4 is the value of x of k. K is equal to minus 1. So two things here. So this particular problem, we knew that it had only one frequency component. Means only two impulses we are going to get, one on the right side, one on the left side. And we are not solving this by substituting in the formula of the Fourier series, but Fourier representation, the inverse Fourier series. So first thing what we do, we represented in terms of complex exponentials, we compare it with the standard expression. For that, you have to find the period and the fundamental frequency first. And here we have the answer. Okay, here we have the answer. So how does the signal look like? What does it contain? See here, so cos pi by 2. So this contains one frequency. Okay, in terms of the fundamental frequency, there is only one frequency, the fundamental frequency at 1, whose amplitude is 3 by 2. But phase, what is the phase of e to the power j theta? What is the magnitude of 3 by 2 e to the power j theta? Magnitude is 3 by 2. What is the phase of e to the power j theta? Phase of e to the power j theta is theta. So e to the power j minus pi by 4 at k is equal to minus 1, it is pi by 4. K is equal to 1, this is sorry, k equal to minus 1, it is minus pi by 4. K equal to 1, it is pi by 4. Okay, what this particular thing? See, only single signal. So what did you get here? One impulse on the right side, one impulse on the left side. Okay, are you cool with this? Now two types of problems you saw. One where you substitute in the formula for the Fourier series. Second one where you substitute, no, you compare with the standard inverse Fourier series expression. Now on the same grounds, let us see one more. Okay, now here is one. Now you tell me, somebody tell me, in this particular question here, this, okay, now here, you tell me how many frequencies are there in this? Sine 3 pi t, cos 4 pi t. There's two waves, right? There are two waves. So there is one frequency for this one, another frequency for this one. Now what you have to do, you have to determine the fundamental frequency of the first wave, or the fundamental period. So author has done it for us. For the first wave, the fundamental period is 2 by 3. Do you agree? How do you find the fundamental period, by the way? A sine of a plus 2 pi fc t. Okay, cos 2 pi fc t. Okay, cos 2 pi fct is the uh, template with which you have to compare. Okay, with which you have to compare. So t1 is 2 by 3, t2 is 1 by 2. So in terms of a period you are doing, it will be LCM. In terms of frequency, it will be GCD. So LCM is 2, so omega naught is pi. So now what I will do is I will simply compare this with I will represent sine and cos in terms of complex exponentials. So sine theta is e to the power j theta plus e to the power minus e to the power minus j theta divided by 2j. Okay, sine theta is e to the power j theta minus e to the power minus j theta divided by 2j. Cos theta is e to the power j theta plus e to the power minus j theta divided by 2. When I do that, then I will separate this. Okay, here. Okay, so what I will do is, okay, so what I will do here is I will okay, so now this thing can crash anytime. So I will send you an invite. Okay, once again, please wait. Okay, okay. Anyway, so x of t equal to x of k. I will send you an invite. Hold. Okay, in a minute. Okay, be there. Okay, be there. Okay, I close this thing and I will